Imagine a world where the apps you use every single day, your favorite streaming service, that social media platform you scroll through constantly, even your banking app, they handle millions of users, process mind-boggling amounts of data, and yet somehow they seem to never, ever go down. It feels almost like magic, doesn't it?
It really does, but spoiler alert, there's no magic, just, well, brilliant engineering.
Today on the Deep Dive, we're pulling back the curtain on how that's even possible. This deep dive is your shortcut, extracting the most crucial insights, the real aha moments from sources like Modern Distributed System Design Fundamentals and the Architect's Playbook, Designing and Scaling Complex Systems.
Right. Our mission is basically to demystify how these incredibly complex systems are built, how they handle immense scale, and, how they manage to stay online even when things inevitably go wrong.
Exactly. We're going to try and cut through the jargon and leave you feeling truly well-informed about the foundational principles and practical strategies behind, well, robust system design. Let's start with the bedrock of it all.
What's truly fascinating is that at the core of every distributed system lies a set of fundamental, unavoidable trade-offs. You can't actually have everything, and accepting these limitations is the very first step toward designing anything resilient.
So to really understand that, we have to talk about what's often called the immutable law of distributed systems, the CAP theorem, also known as Brewer's theorem. Can you explain what CAP stands for, but maybe more importantly, why it's considered, well, immutable?
Absolutely. So CAP stands for consistency, availability, and partition tolerance. Consistency, C, in this context, means strong consistency, or linearizability, technically.
Right. So strong consistency, what does that mean?
It guarantees that after a successful data write, any subsequent read from any part of the system will always return that new, updated value. Think about financial transactions. If you transfer money, you need to know your balance reflects that change immediately, everywhere. It has to be right.
Makes sense. And availability.
Then there's availability A, which guarantees that every request sent to a non-failing server receives a response. The system stays operational and responsive, even if the data it provides might not be the absolute latest, it just needs to answer.
Okay, stays up. And the last one, partition tolerance.
And finally, partition tolerance, P, is the system's ability to keep working despite network failures, partitions, which essentially, cut off communication between different parts of your system, like servers in different data centers losing connection.
And here's the crucial insight that modern distributed system design fundamentals really drives home. In any real-world distributed system spanning multiple servers or data centers, network failures aren't just a possibility. They're an absolute certainty. So, given that inevitability, is it fair to say that P partition tolerance is essentially mandatory?
Precisely. P is non-negotiable for any truly distributed system. You just have to plan for network failures, which means the real-world dilemma, the actual choice you make, is always between consistency and availability when a network partition occurs.
Ah, okay. So you choose between C and A because P is a given.
Exactly. You can opt for a CP system, prioritizing consistency and partition tolerance. Data integrity comes first. If a node can't guarantee it has the most recent data because of a partition, it will error out or time out rather than give potentially wrong data.
Like the financial systems you mentioned.
Right. You don't want your bank showing the wrong balance during a network glitch.
Definitely not.
On the other hand, you can choose an AP system availability and partition tolerance. This prioritizes responsiveness. It will respond with the best data it has, even if it might be slightly stale, with the promise that eventually, once the partition heals, all data will converge.
And that sounds like social media feeds, where seeing something quickly is maybe more important than it being perfectly up to the second.
Exactly. Social media feeds, product recommendations, things where uptime and responsiveness feel more critical than immediate, absolute consistency across the globe.
So it sounds like it's less about a technical right or wrong choice and more about aligning technology with the business's tolerance for different types of failure, which failure hurts more.
That's a perfect way to put it. But the Architect's Playbook takes us a step further with the PACELC theorem. It adds another layer.
PACELC, okay, what does that add to the picture?
It adds nuance. PACELC explains that if a partition occurs, you trade between availability and consistency. That's the PAC part, just like CAP.
Okay.
But else, meaning in the absence of a partition during normal operation, you also have to trade between latency and consistency.
Ah, so even when things are working fine, there's still a trade-off involving consistency.
Right, because strong consistency, even when everything is healthy, often means higher latency. Think about it. Writes might have to be acknowledged by multiple nodes before succeeding. That takes time, adds overhead.
So you might gain that stronger consistency, but you pay for it in performance and speed, even on a good day.
Exactly. It's not just about failure modes.
That brings us to another crucial point. Consistency isn't just one thing. You said CAP means strong consistency, but it's actually a whole spectrum, right? Not just the C in CAP. This can get confusing quickly.
It definitely can. While CAP's C generally refers to strong consistency or linearizability, there are many more nuanced models out there.
Like what?
Well, strong consistency, linearizability, exemplified by systems like Google Spanner maybe, or traditional databases configured just right, ensures every read gets the absolute most recent write, as if there were only one copy of the data. It's the most stringent and often the slowest.
Okay, the gold standard, but maybe pricey. What else?
A slightly more relaxed option is sequential consistency. Here, operations appear in some single total order across all nodes, but it's not necessarily tied to real-time. Think maybe distributed queues, where the exact real-time order doesn't matter quite as much as ensuring operations are processed in a consistent sequence across all workers.
Interesting. What's next?
Then you have causal consistency. This is important. It ensures that operations with a clear cause and effect relationship are seen in the correct order by everyone.
Like a reply to a comment. You have to see the comment first.
Precisely. Social media threads are a great example. Collaborative editors like Google Docs also rely heavily on this to make sense. You need to see edits in an order that respects causality.
Okay, that makes intuitive sense. And the most relaxed.
That would be eventual consistency. This basically guarantees that if no new updates occur for a while, all replicas will eventually converge to the same state. During that convergence period, though, different nodes might return stale data. But eventually, everything settles down.
And this is where base comes in.
Exactly. Eventual consistency is the foundation of basically available, soft state, eventual consistency. It's incredibly common in AP systems like Amazon DynamoDB or Apache Cassandra. Think social media likes, view counts, product availability, where momentary inconsistency is acceptable for better availability and performance.
Okay, so just to recap, if you're building an AP system, you're usually leaning on eventual consistency. If it's CP, you're enforcing strong consistency. That makes a lot of sense.
Generally speaking, yes, that's the typical alignment.
Now, how do we measure if these systems are actually performing well? What are the key metrics that tell us if our brilliant design is actually, working in the real world?
The two core metrics you always hear about are latency and throughput.
Right, latency first.
Latency is the time it takes for a single request to make a round trip from initiation to receiving a response, usually measured in milliseconds, ms. It's what you feel as a user, the lag in an online game, or the delay loading a web page or executing a trade, user-facing delay.
Got it. And throughput.
Throughput, on the other hand, measures the amount of data or the number of operations a system can process within a given time period. Think requests per second, RPS, or maybe bits per second for streaming. This is vital for systems like video streaming, where you need to deliver massive amounts of data, or maybe bulk data processing jobs where the total volume of work completed per hour is key. System capacity.
And often there's an inverse relationship, right? Like if you batch things up to process more data overall, that might increase throughput, but make each individual item take longer, increase its latency.
That's a very common trade-off, yes. Batching is a classic example.
Is there ever a silver bullet or strategies that can help with both?
Well, sometimes you can improve both, depending on the bottleneck. For example, effective caching, using something like Redis or Memcache, dramatically reduces latency for cached items by avoiding slower database lookup.
Okay, faster responses.
Right. And by offloading all those read requests from your primary database, the database now has more capacity to handle writes or more complex queries, potentially increasing its overall throughput too.
I see. So relieving one bottleneck helps elsewhere. What about scaling?
Horizontal scaling, just adding more servers, clearly improves overall throughput because you have more machines working in parallel. But if managed well with a load balancer, it can also reduce latency because individual servers are less likely to be overloaded.
Okay, so spreading the load helps both capacity and speed.
Often, yes. Other things too, like optimizing code, database queries, reducing network hops for latency. For throughput, asynchronous processing using message queues is huge, or simply increasing network bandwidth. It's all about finding the bottleneck and applying the right tool.
So latency is often user-facing. It's the lag you feel.
Yeah.
Throughput is more system-facing. It's the system's overall capacity, and that really helps frame it.
That's a good way to think about it.
Now let's talk about how these systems are actually structured. There's a big architectural choice that shapes everything. The classic debate between monoliths and microservices.
Ah, yes, the great debate. This is one of the most foundational decisions for any significant application. A monolithic architecture is, well, like it sounds, a single, unified, self-contained unit. All the different functionalities are tightly coupled together in one large code base and deployed as one single executable or application.
And the appeal there is simplicity, at least at first.
Exactly. For small applications, or maybe startups just validating an idea, an MVP, it's often simpler to develop, deploy, and debug initially. You don't have the overhead of managing multiple services and network communication. It can be surprisingly efficient early on.
But the problems come later, as it grows.
That's the common story, yes. As the architect's playbook points out, as a monolith grows, it can become incredibly difficult to manage. Development velocity often slows down because changes in one area can unintentionally break things elsewhere. Testing becomes a huge effort.
And scaling must be harder.
Much harder. It's difficult to scale individual components independently. If your user authentication needs more power but your reporting module doesn't, you still have to scale the entire monolith. A single bug can potentially crash the whole application. And adopting new technologies, maybe a better database for one specific feature, becomes a massive, often risky undertaking for the whole system.
Okay, so that leads us to the alternative.
Yeah.
Microservices architecture. What's the core idea there?
The core idea is to structure an application as a collection of small, loosely coupled, independently deployable services. Each service typically focuses on a specific business capability like inventory or user profiles or recommendations.
And they're truly independent.
Ideally, yes. Each often has its own code base, maybe its own dedicated team, and crucially can even have its own database. They communicate with each other over a network, usually via well-defined APIs.
And the advantages are basically the flip side of the monolith's cons.
Pretty much. You get independent development and deployment, which allows for much faster, more agile delivery by smaller teams. You can scale individual services based on their specific needs. You gain improved resilience through fault isolation. If one service fails, that doesn't necessarily bring down the entire application.
And technology flexibility.
Big one. You can choose the best technology stack, language, database, whatever for each specific service's job, rather than being locked into one stack for everything.
And we've seen this play out in the real world with major migrations. Amazon, Netflix, Uber, they all famously started with monoliths and then made the often painful transition to microservices.
Absolutely. It's a common pattern for successful large-scale systems.
I remember reading about a financial services CRM that used the strangler fig pattern. They didn't do a big bang rewrite. They gradually carved out pieces, starting with a major performance bottleneck. I think it's a 10-hour data dump process, and replace that with a service first, sort of de-risking the transition step by step.
That's a very smart strategy. The strangler fig pattern, gradually replacing parts of the monolith, is often much safer than a complete rewrite.
But I've also heard warnings about the distributed monolith. What exactly is that, and how do companies accidentally fall into that trap? It sounds like you get the downsides of both worlds.
That's an excellent question and a very, very common pitfall. A distributed monolith is essentially when you've adopted a microservices architecture. On paper, you have separate services, but they are still tightly coupled.
How so?
Maybe they share a single massive database, so changes to the schema affect multiple services. Or maybe services make lots of synchronous calls to each other, creating complex runtime dependencies. Or maybe deploying one service requires deploying 3 others at the exact same time.
You haven't really decoupled them.
Exactly. You've just moved the coupling from inside one code base to across a network, which often makes things harder to debug, deploy, and operate because now you have network latency and failures involved too. The complexity isn't reduced, it's just reorganized and often amplified.
So the takeaway is microservices aren't a silver bullet. They require real discipline and operational maturity.
Absolutely. It's often the right choice for larger organizations with multiple independent teams, but it's a significant undertaking. Monoliths can still be perfectly fine, even preferable for startups or simpler applications.
So we understand the foundational rules, the trade-offs like CAP, and the big architectural choices like monolith versus microservices. But let's get practical. If microservices are all about independence, How do they really talk to each other effectively without just creating a new, more complex spaghetti of direct connections? What's the clever design pattern that solves that? This is where it gets really interesting, I think.
It really is. And the answer very often is event-driven architecture. EDA.
Okay.
It's a design pattern where services communicate asynchronously through events. An event is basically just a message signifying that something significant has happened, a state change, like an order-placed event or a user-registered event.
And how does that promote independence?
It promotes incredible loose coupling. Services don't directly call each other's APIs in a synchronous way. Instead, one service, the event producer, simply publishes an event to an intermediary saying, hey, this happened. Then other services, the event consumers or subscribers who are interested in that type of event, listen for it and react accordingly. The producer has no idea who, if anyone is listening, it just broadcasts the fact.
So they don't need to know about each other directly.
Exactly. This enables highly asynchronous communication, which dramatically boosts responsiveness and throughput because services aren't waiting on each other. It also greatly improves scalability and resilience. You can add new consumers later that react to existing events without ever changing the original producer.
So what are the core components you need to make an EDA work? You mentioned producers and consumers.
Right. You typically have the event producers, which are the services generating and publishing these events. You have the event consumers, subscribers, listening for specific events and executing their logic when they receive one. Maybe an inventory service listens for order place to decrement stock, or a notification service listens to send an email.
And the intermediary. How do events get from producers to consumers?
That's the crucial third piece, the event broker or event router. This is a dedicated piece of infrastructure, like Apache Kafka or RabbitMQ, that acts as the intelligent intermediary. It ingests all the events from producers and reliably routes them to all the interested consumers based on subscriptions or topics.
And you mentioned Uber earlier. Is their architecture a good example of this?
It's a fantastic example. When a user requests a ride, their system generates a single ride requested event. That one event is then consumed in parallel by multiple completely independent services, the matching service looking for drivers, the ETA service calculating arrival time, the pricing service determining the fare all without making direct synchronous calls to each other.
So the ride service just fires the event and forgets about it, essentially.
Pretty much. This choreography, as it's sometimes called, enables massive scalability and agility. They can add a new service, say, for fraud detection, that also listens to ride-requested events without touching any of the existing services. It's incredibly powerful for evolving complex systems.
Speaking of scalability, the data layer, the databases, that's often the hardest part to scale in any distributed system, right? What are the primary strategies there?
Oh, absolutely. Scaling the database is frequently the biggest bottleneck. When it comes to that, two primary strategies really stand out: replication and sharding.
Okay, let's start with replication. What's that?
Replication is essentially about making multiple identical copies of your database. Typically, you have a master database instance that handles all the write operations, inserts, updates, deletes. These writes are then replicated or copied to one or more slave database instances.
And the slaves are usually read-only.
Usually, yes. The main purposes of replication are high availability and disaster recovery. If the master fails, a slave can be promoted to take over. And it's fantastic for read scaling because you can distribute all your read queries across those multiple slave replicas, taking load off the master.
But it doesn't help with write load. The master still has to handle all the writes.
Exactly. The master can still become a write bottleneck, especially for applications with very high write volumes. All writes have to go through that single point.
So if writes become the problem, that's where sharding comes in.
That's precisely when you start seriously considering sharding, which is also known as horizontal partitioning.
Okay, how does sharding work?
With sharding, you split a very large database into smaller independent pieces called shards. Each shard holds a unique subset of the total data. For example, you might shard your users table based on user id. Users 1000 might be on shard 1, users 1001, 2000 on shard 2, and so on.
And each shard is basically its own mini database.
Effectively, yes. Each shard can live on its own server or cluster. The key is that data is partitioned based on a shard key, like that user id. There are different ways to determine the key: key-based or hashed partitioning, range-based partitioning, or even directory-based, where a lookup service tells you which shard holds which data.
And the main benefit here is write scaling.
Yes, primarily. It distributes the write load across multiple independent database instances, because writes for different users go to different shards. It's also essential for handling truly massive data sets that simply won't fit on a single machine, regardless of write volume.
But it sounds more complex than replication.
Oh, definitely. Choosing the right shard key is critical to avoid hotspots where one shard gets overloaded. Rebalancing data if you need to add more shards can be tricky, and queries that need data from multiple shards become much more complex to execute.
So what do most large-scale systems do? Pick one or the other.
Most really effective large-scale systems actually combine both. They shard their database into multiple logical clusters, distributing the right load, and then within each shard cluster, they use replication. Each shard has a master handling rights for that shard's data and multiple read replicas for availability and read scaling within that shard.
Ah, okay. So sharding for write distribution and replication within each shard for reads and availability. Best of both worlds.
Exactly. It gives you both write scalability across shards and read scalability plus resilience within each shard.
Once you've horizontally scaled your application servers and your databases by adding more instances, you need a way to manage all that incoming traffic and distribute the load efficiently. That's where load balancers become essential, right? How do they act as the traffic cops of the system?
That's a great analogy. Think of load balancers as the intelligent traffic cops sitting in front of your pools of servers. Their job is to receive incoming requests and distribute them across the available healthy servers in the pool, preventing any single server from getting overwhelmed.
And how do they decide where to send each request? Are there different strategies?
Yes, there are various algorithms they can use. You have static algorithms, which are simpler. Round robin just sends requests to servers sequentially. Server 1, then server 2, then server 3, and back to 1. Weighted round robin is similar, but lets you assign weights so more powerful servers get proportionally more requests.
What about sticky sessions? If a user needs to stay on the same server?
Right, for that you might use IP hash. The load balancer calculates a hash of the client's IP address and uses that to consistently send requests from that IP to the same backend server. This helps maintain session states stored on that specific server.
Okay, those are static. What about dynamic ones?
Dynamic algorithms are more intelligent because they consider the current state of the servers. Least connection sends the next request to the server that currently has the fewest active connections, assuming it's the least busy. Least response time is even smarter. It sends requests to the server that is currently responding fastest, factoring in both connection count and server processing speed.
That sounds more adaptive. Now, I've heard about layer 4 versus layer 7 load balancing. What's the crucial distinction there, and why is layer 7 supposedly so important for microservices?
That's a really important distinction. A layer 4 load balancer operates at the transport layer of the network model. It makes decisions based purely on network information like IP addresses and port numbers, TCP UDP.
Okay.
It's very fast because it doesn't look inside the packets, but it's essentially blind to the application content.
Okay, fast but simple.
Right. A layer 7 load balancer, on the other hand, operates at the application layer. This means it can actually inspect the content of the requests, like HTTP headers, URLs, cookies, etc.
And that lets it do smarter routing.
Exactly. It enables powerful content-aware routing. This is key for microservices architectures. For instance, a layer 7 load balancer, often implemented as part of an API gateway, could route all requests with a URL path starting App-a-Video to a dedicated pool of video processing microservices, while requests to Epic users go to the user service pool.
Ah, I see. So it can direct traffic based on the function the user is trying to access, not just distribute load blindly.
Precisely. You can also use it for things like A/B testing, routing a percentage of users to a new version based on a cookie, or handling SSL termination or rewriting headers. It offers much more sophisticated traffic management capabilities, which are invaluable when you have many independent services.
Another critical performance tool in the scaling toolkit is caching. We touched on it briefly, but let's dive deeper. What exactly is it, and how is it strategically used in a distributed system to boost performance?
Caching is fundamentally simple in concept. It's storing frequently accessed data in a high-speed, temporary storage layer, usually RAM, to avoid the slower process of fetching it from its primary source, like a database on disk or an external API call. The goal is speed.
And you can cache at different places in the system, right?
Absolutely. There are multiple layers where caching can be effective. Your browser cache stores static assets, like images and CSS files, right on the user's machine. Content delivery networks, CDNs, cache static public content like videos, images, JS libraries, and servers geographically distributed around the world, closer to your users, reducing latency significantly for global audiences.
And then closer to the application itself.
Right. You have application caches or in-memory caches. These run on or near your application servers and are used to store dynamic data or frequently requested results from database queries or computations. This is where you'd store things like user session data, results of complex calculations, or frequently accessed product details. CDN for public static stuff, application cache for dynamic, often user-specific stuff.
And there are common patterns for how applications interact with these caches, right? Like how they decide what to put in the cache and when.
Yeah. Yes, there are several common patterns. The most frequent is probably read-aside, sometimes called lazy loading. The application logic goes like this. First, check the cache for the data you need. If it's there, a cache hit, great, use it. If it's not there, a cache miss, then read the data from the primary database, store a copy in the cache for next time, and then return it.
So you only load into the cache when it's actually needed.
Exactly. Then there's write through. In this pattern, when the application writes data, it writes it to the cache and synchronously to the database before returning success. This ensures the cache is always consistent with the database, but it adds a bit of latency to your write operations because you're doing two writes.
Okay, consistent but slower writes. What's the alternative for faster writes?
That would be write back, sometimes called write behind. Here, the application writes data only to the cache and returns success immediately. The cache then asynchronously writes the data back to the primary database sometime later. This gives you very fast writes, but carries a risk. If the cache server fails before the data is persisted to the database, that data could be lost.
High risk, high reward, potentially.
Sort of, yes. It depends on the data's tolerance for loss.
Now, it's often said that cache invalidation is one of the two hardest problems in computer science, along with naming things. Why is keeping the cache up to date so notoriously difficult, especially in distributed systems? And what's a common mistake people make?
Yes, naming things and cache invalidation. It's notoriously difficult because you're trying to maintain consistency between two different data stores, the fast cache and the slow source of truth, in an environment where data can change frequently and unpredictably, and where network delays or failures can happen.
So the core problem is stale data.
Exactly. If data in the database changes, how and when do you update or remove the old copy from the cache? If you don't do it correctly or quickly enough, your application might serve stale, outdated information to users, which can range from annoying to critically wrong depending on the context.
And the common mistake.
A very common mistake is overly aggressive caching, setting very long time-to-live TTL values on cached items without having a robust, explicit invalidation strategy. People rely too much on just letting items expire naturally via TTL, but if the underlying data changes frequently within that TTL window, users see stale data. You often need a way to actively remove or update items from the cache when the source data changes.
And for distributed systems, you need distributed caches, right? Like Redis versus memcached. What's the difference there?
Yes, when you have multiple application servers, you typically need a shared distributed cache that all servers can access. Redis and memcache are the two most popular choices. Memcache is generally simpler. It's a high-performance distributed key-value cache, primarily designed for caching simple strings or objects. It's very fast, but generally volatile data is lost if the server restarts.
Okay, simple and fast. Redis.
Redis is often described as more of an in-memory data structure store. While it's excellent as a key-value cache, it also natively supports more complex data structures like lists, sets, sorted sets, hashes, and streams. It offers features like persistence, saving data to disk, replication for high availability, and built-in support for things like pub/sub messaging. It's generally more feature-rich and versatile than memcached.
So Redis, if you need those extra features or data structures, memcached for pure, simple, fast key-value caching.
That's a reasonable starting point, yes. The fundamental trade-off in caching, regardless of the tool, always comes back to that balance. Latency reduction versus the potential for data inconsistency, staleness, and how you manage that through TTLs and invalidation.
Let's talk about asynchronous communication again, specifically in those event-driven microservices we discussed. When you need services to talk without tight coupling, message brokers are key. How do Apache Kafka and RabbitMQ compare? They seem to be the two biggest players in that space.
They are indeed the heavyweights, but they come from quite different philosophies and are optimized for different use cases. RabbitMQ is often seen as the more traditional smart message broker. It implements protocols like AMQP, Advanced Message Queuing Protocol.
Smart broker, what does that mean?
It means the broker itself has a lot of intelligence regarding message routing, delivery guarantees, and queue management. It typically uses a push-based model where the broker actively pushes messages to consumers. Messages are often treated as ephemeral. Once a consumer acknowledges processing a message, it's usually deleted from the queue.
And what's RabbitMQ good at?
It excels at complex message routing scenarios, like routing based on headers or topics with wildcards, managing work queues where multiple consumers pull tasks off a queue, and ensuring guaranteed delivery of individual messages to specific consumers. Think traditional background job processing or tasks that need reliable point-to-point or specific routing logic.
Okay, so smart broker, push model, complex routing, often ephemeral messages. How does Kafka differ?
Apache Kafka is fundamentally different. It's better described as a distributed streaming platform or maybe a distributed commit log. It acts more like a dumb broker with smart consumers.
Dumb broker.
Meaning the broker itself has simpler routing logic, mainly based on topics and partitions. The intelligence lies more in the consumers, which track their own position offset in the log. Kafka uses a pull-based model where consumers actively pull data from the broker.
And the messages.
Critically, messages in Kafka are durable and persistent by default. They aren't deleted immediately after being read. They're retained in the log based on a configurable retention policy like time or size. This allows multiple different consumer groups to read the same stream of events independently and even replay events from the past.
So message replay is a key difference. What's Kafka optimized for?
Kafka is designed for extremely high throughput, handling millions of messages per second. It's ideal for building real-time event streaming pipelines, log aggregation, collecting logs from many sources, change data capture from databases, and any scenario where you need to process a continuous stream of events reliably and potentially have multiple independent systems react to that same stream.
So if you're thinking traditional task queues, complex routing rules, maybe guaranteed delivery of individual messages for specific short-lived tasks, RabbitMQ might be a better fit.
Generally, yes.
But if you're building high-throughput event streams, need message durability and replayability, or want to decouple multiple systems reacting to the same data flow, Kafka is likely the way to go.
That's a good summary. The architectural pattern and the specific needs, throughput, durability, writing complexity, replayability, really dictate which tool is more appropriate. They solve related but distinct problems.
Designing these complex systems is one thing, but operating them reliably at scale in production is a whole other challenge. That's where the DevOps mindset really comes into play, starting with CI/CD continuous integration and continuous deployment, specifically for microservices. It's fundamentally different from how you'd manage CI/CD for a monolith, isn't it?
It absolutely is. The core promise of microservices is independent deployability, so your CI/CD practices must support that. The foundational principle is to isolate CI/CD pipelines per service. Each microservice needs its own completely independent pipeline for building, testing, and deploying.
Why is that so critical?
Because it decouples the release cycles. Team A, working on the search service, can deploy their changes multiple times a day without waiting for or coordinating with Team B working on the payment service. This dramatically accelerates development velocity and, importantly, reduces the blast radius. If a deployment goes wrong, it only affects that one service.
Okay, so independent pipelines, what else is key?
You really need to containerize everything, almost always using Docker. Packaging each microservice and its dependencies into an immutable container image ensures consistency across all environments: the developer's laptop, testing, staging, production. It works on my machine, largely disappears.
And testing must be different, too.
Hugely different, and arguably more critical. You need to automate a comprehensive, multi-layered test suite. This includes fast unit tests for individual components, but also contract tests to verify that services adhere to their API agreement with other services, integration tests to check interactions between a few key services, and potentially performance tests, all running automatically in the pipeline.
And for the actual deployment to production, it's not just a big bang release anymore with microservices, is it? How do companies manage the risk associated with these frequent independent deployments?
No, you absolutely avoid big bang releases. Instead, you implement progressive delivery strategies to manage that risk systematically. Think canary deployments, where a new version is initially released to only a small subset of users or servers. You monitor it closely, and if it looks good, you gradually roll it out to everyone. If not, You roll back quickly with minimal impact.
Or blue-green.
Or blue-green deployments. Here, you deploy the new version to an identical parallel production environment, the green environment. Once it's tested and ready, you switch the load balancer to instantly direct all traffic from the old blue environment to the new green one. This gives you near-instant deployment and rollback capability.
That sounds powerful. Any other key practices?
Increasingly, teams are embracing GitOps. This means your Git repository becomes the single source of truth defining the desired state of your production environment. For example, which service versions should be running. Automated agents then constantly work to ensure the actual environment matches the state defined in Git. And finally, you have to secure the pipeline itself. Shift-left security means incorporating things like container vulnerability scanning and secure secret management, using tools like HashiCorp Vault or Kubernetes secrets early in the development process, not as an afterthought.
So the ultimate goal is making deployments for each service frequent, automated, reliable, and above all, safe.
That's the dream, yes. Independent, rapid, and safe deployability for every single service.
When we talk about containerization at scale, the two names you hear constantly are Docker and Kubernetes. They're often mentioned together, but they're not competitors, right? They solve different parts of the containerization puzzle.
Exactly. They complement each other beautifully. They work as a powerful pair. Docker is the tool primarily focused on the packaging part. It allows developers to build lightweight, portable, immutable container images that bundle an application and all its dependencies together.
So Docker creates the standardized box.
Precisely. It solves the build once, run anywhere problem for your application by ensuring the environment inside the container is consistent, regardless of where it runs.
So what does Kubernetes do?
Kubernetes, often abbreviated as KACE, then, is the platform for orchestrating those containers at scale. Once you have your Docker containers, Kubernetes takes over managing their entire lifecycle across a cluster of machines, physical or virtual.
Managing the lifecycle, what does that involve?
It involves everything needed to run containers reliably in production, deployment, rolling out new versions, scaling, automatically adjusting the number of container instances based on load balancing, distributing traffic across instances, service discovery, allowing containers to find and talk to each other, storage orchestration, and crucial self-healing capabilities.
Self-healing sounds important.
It's incredibly powerful. If a container crashes, Kubernetes automatically restarts it. If an entire server node fails, Kubernetes reschedules the containers that were running on it onto healthy nodes in the cluster. It constantly works to maintain the desired state you've defined.
So the typical workflow is developers build Docker images containing their microservices, push those images to a container registry, like Docker Hub or a private one, and then they tell Kubernetes, run this image, I want 3 copies, keep them healthy, and expose them via this network address.
That's exactly the standard workflow. Kubernetes provides key abstractions that make this possible. Pods, which are the smallest deployable units, usually containing a single application container, though sometimes more. Deployments, which manage a set of identical pods, handling updates and scaling. And services, which provide a stable virtual IP address and DNS name for a set of pods, abstracting away the fact that pods can come and go.
So Kubernetes essentially provides this layer of abstraction over the underlying infrastructure.
Yes, you can think of it as the operating system for the cloud or the operating system for the data center. It provides a consistent self-managing platform for running your containerized applications, regardless of whether you're running on bare metal, VMs, or in a public cloud.
You can't fix what you can't see. That feels particularly true for complex distributed systems. This brings us to observability. It's often described as having 3 pillars: logs, metrics, and traces. How do these pieces fit together to give you a full picture of your system's health?
They each provide a different complementary view. Logs are time-stamped, discrete events that record what happened at a specific point in time. Think of application logs, recording errors, warnings, or specific actions. User X logged in, order Y processed. They're fantastic for detailed debugging and understanding the sequence of events leading up to a problem, usually after the fact.
Okay, detailed event-based records.
Yeah.
Metrics.
Metrics are different. They are aggregated numerical data points collected over time, usually at regular intervals. Think CPU utilization, memory usage, request counts per second, error rates, request latency percentiles like P95, P99. Metrics are great for real-time monitoring, building dashboards to see overall system health, trend analysis, and crucially, for setting up alerts when key indicators cross certain thresholds.
So aggregated numbers for monitoring and alerting. And traces.
Traces focus on the life cycle of a single request as it flows through your entire distributed system. In a microservices world, a single user action might involve calls to 5, 10, or even more different services. A trace stitches together all the operations related to that initial request across all those services, showing how long each step took. This is invaluable for identifying latency bottlenecks.
Why is this request slow? It's spending 80% of its time waiting for the recommendation service and pinpointing failures in complex interactions.
So logs for what happened, metrics for how much or how often, and traces for where the time went or where it broke in a distributed flow. That's a pretty good way to summarize it. They work best together. You might get an alert from a metric, high error rate, then use traces to see which service call is failing within the request flow, and finally dive into the logs of that specific service instance around that time to find the root cause error message.
Now, I've heard people distinguish between monitoring and observability.
Hmm.
Is that just jargon, or is there a real difference?
It's a meaningful difference, though the terms are sometimes used interchangeably. The architect's playbook clarifies this well. Monitoring is generally about tracking known unknowns. You know certain things might go wrong, like disk space running low or high CPU, so you set up dashboards and alerts to watch for those specific predefined conditions.
Okay, watching for expected problems. Observability.
Observability, enabled by having good logs, metrics, and traces, is more about being able to investigate unknown unknowns. It's about having the tools and data richness to ask new questions about your system after something unexpected happens, to explore and understand emergent behaviors or failure modes you didn't anticipate when you set up your monitoring. It allows you to debug novel problems effectively.
So monitoring is dashboarding known failure modes. Observability is having the raw data and tools to debug anything.
In essence, yes. Observability gives you the capability to understand the internal state of your system just by observing its external outputs, logs, metrics, traces, allowing you to navigate from effect back to cause, even for unexpected issues.
And what are the key tools people typically use in the open source world to achieve this level of observability?
For logs, the ELK stack, or now often the Elastic Stack, is very common. Elasticsearch provides the powerful distributed search and analytics engine. Logstash, or alternatives like Fluent, handles collecting, processing, and transforming logs from various sources. And Kibana provides the visualization layer for creating dashboards and exploring log data. Elasticsearch's strength is really its full-text search capabilities.
Okay, ELK for logs. Metrics.
For metrics, Prometheus has largely become the industry standard, especially in the Kubernetes ecosystem. It uses a pull-based model where it actively scrapes metrics endpoints exposed by your applications and infrastructure. It has an efficient time series database optimized for metrics data and a very powerful query language called PromQL. It also integrates with Alert Manager for sophisticated alerting based on those metrics.
Prometheus for metrics and alerting, and putting it all together visually.
That's where Grafana comes in. Grafana is the de facto standard for visualization and dashboards. Its real power is that it can connect to multiple different data sources, Prometheus for metrics, Elasticsearch for logs, databases, cloud provider APIs, and many others, allowing you to build unified dashboards that combine data from all your observability pillars into a single pane of glass.
So you might have a Grafana dashboard showing Prometheus metrics alongside relevant logs from Elasticsearch for a particular service.
Exactly. That unified view is incredibly valuable for quickly correlating different types of information during an incident investigation.
The API, the application programming interface, that's really the contract that binds all these systems together, especially in a microservices world. Let's talk about the modern API paradigms people use: REST, GraphQL, and gRPC. They seem to serve different purposes. When would you choose one over the others?
That's right. They each have their strengths and weaknesses. REST, representational state transfer, isn't a strict protocol, but more an architectural style that's been dominant for web APIs for a long time. It's resource-oriented, uses standard HTTP methods like get, post, put, delete, acting on URLs that represent resources, like users 123 or products.
And its pros and cons.
REST is simple, widely understood, leverages HTTP caching well, and is great for public APIs or simple CRUD, create, read, update, delete operations. However, it often leads to overfetching, getting back more data fields than the client actually needs, or underfetching, needing to make multiple API calls to gather all the data required for a single view.
The classic N+1 problem sometimes. So that's where GraphQL comes in.
Exactly. GraphQL is a query language for APIs and a runtime for fulfilling those queries. Instead of multiple endpoints for different resources, GraphQL typically exposes a single endpoint, like GraphQL. The client specifies exactly what data fields it needs, potentially traversing relationships between different data types, all in a single query.
So the client is in control of the data shape.
Precisely. This solves the overfetching and underfetching problems inherent in REST. It's fantastic for applications with complex data needs, especially mobile apps or sophisticated front ends, where network efficiency and tailored data payloads are crucial. It's also great for enabling rapid front-end development without constantly needing back-end changes for new data requirements. Think back-end for front-end, BFF patterns.
Okay, GraphQL for flexible, client-driven data fetching. What about gRPC? It sounds different.
It is quite different. gRPC Remote Procedure Call, is a high-performance RPC framework developed by Google. It uses protocol buffers, protobufs, as its interface definition language and serialization format. Protobufs are a binary format, which is much more compact and faster to parse than text-based formats like JSON used by REST and GraphQL.
And it runs over HTTP too.
Yes, it leverages HTTP2 for features like multiplexing, multiple requests over a single connection, and bidirectional streaming, making it very efficient. gRPC is primarily designed for high-performance, internal machine-to-machine communication between microservices, where low latency and high throughput are critical, and where you control both the client and the server.
But maybe less suitable for browser-based apps directly.
Traditionally, yes, because browsers don't natively speak protobuf or fully support HTTP2 trailers required by gRPC. While there are solutions like gRPC Web that act as a proxy, it adds complexity compared to REST or GraphQL for direct browser communication.
So the guideline is REST for general-purpose public APIs, simple CRU day, leveraging HTTP standards. GraphQL for flexible data fetching, complex front-ends, mobile apps, BFFs, and gRPC for high-performance internal microservice-to-microservice communication, where efficiency is paramount.
That's a very good rule of thumb, yes. The choice depends heavily on the specific use case, the consumers of the API, browsers, mobile apps, other services, and the performance requirements.
Beyond just the style or paradigm, how do you make APIs truly resilient and robust, especially when dealing with the unpredictable nature of distributed systems and networks? We're talking about fundamental concepts like idempotency, versioning, and rate limiting. How critical are these?
They are absolutely essential for building APIs that can withstand real-world conditions and evolve gracefully. Let's start with idempotency. This is crucial in distributed systems where network requests might fail and need to be retried.
What does idempotency mean exactly?
An operation is idempotent if calling it multiple times has the exact same effect and returns the same result as calling it just once successfully. Think about it. If you retry a request because you didn't get a response, you need assurance that retrying won't accidentally perform the action twice.
Right, like charging a credit card twice.
Exactly. HTTP methods like get, put, which replaces a resource entirely, and delete are inherently idempotent by definition. You can get a resource or delete it multiple times. The end state is the same after the first successful call. But post, which typically creates a new resource, is not idempotent by default. Sending the same POS twice might create two identical resources.
So how do you make potentially non-idempotent operations safe to retry, like creating an order?
The standard practice is for the client to generate a unique idempotency key, often a UID, and include it in the request header. Is a idempotency key some unique value? The server then stores the result of the operation associated with that key for a certain period. If it receives another request with the same key, instead of processing it again, it simply returns the stored result from the first successful operation.
No.
This makes even POST requests safe to retry.
Ah, clever. Okay, what about API versioning? Why is that needed?
API versioning is how you manage changes to your API over time, especially breaking changes, without disrupting existing clients that rely on the older version. As your system evolves, you'll inevitably need to change API contracts, maybe rename a field, change a data type, or alter behavior.
Then you can't just change it and break everyone using the old version.
Right. You need a strategy to allow clients to opt into newer versions while maintaining compatibility for older clients for a period. Common versioning strategies include putting the version number in the URI path, like V1 products versus V2 products. This is probably the most common and clearest approach. Others use a query parameter, products.version2, or a custom HTTP header, except version.v2.
Any best practices there?
Version your API from the beginning, even if it's just V1. Use semantic versioning, major.minor.patch, to indicate the type of change, major for breaking changes, and clearly communicate your version strategy and deprecation policy to your API consumers. Give them time to migrate.
Makes sense. And rate limiting. That sounds like protection.
It is. Rate limiting is crucial for controlling how many requests a client can make to your API within a given time window. For example, 100 requests per minute. Its primary purpose is to protect your backend services from being overwhelmed, whether by accidental infinite loops in client code, denial of service attacks, or simply ensuring fair usage among all clients.
How is it typically implemented?
Common algorithms include the token bucket. Clients consume tokens from a bucket that refills at a fixed rate, or sliding window log counter. When a client exceeds their limit, the API should return an HTTP 429 too many request status code, ideally with a retry after header indicating when they can try again.
And one last thing here, input validation. Seems basic, but probably vital.
Absolutely vital. It's your very first line of defense against a huge range of security vulnerabilities like SQL injection, cross-site scripting, XSS, and unexpected errors. Always validate all incoming data from clients or other services as early as possible. Check data types, lengths, formats, allowed characters or values. Use schema validation tools like JSON schema to define and enforce the expected structure. And always prefer whitelisting allowed inputs over trying to blacklist bad inputs. It's much safer.
So, idempotency for safe retries, versioning for evolution, rate limiting for stability, and validation for security. All critical for robust APIs.
Couldn't have said it better myself.
And finally, securing these APIs. Authentication and authorization are key. Let's quickly distinguish between those two as they often get conflated.
But they are different. Authentication often is about verifying who you are. It's the process of proving your identity, typically by providing credentials like a username and password, or maybe using a biometric factor. The system confirms you are the user you claim to be.
Okay, proving identity. Authorization.
Authorization, auth comes after authentication. It's about determining what you are allowed to do once your identity has been confirmed. Based on your role or permissions, what resources can you access? What actions can you perform? Can you read data? Can you write data? Can you delete data?
Who you are versus what you can do.
Yeah.
Got it. So in the context of securing APIs, what are the common technologies or standards used? I hear about JWT and OAuth 2.0 all the time.
Yes, those are two very important and often complementary technologies. Let's start with JSON Web Tokens, JWTs. A JWT is a compact, URL-safe, self-contained standard for representing claims securely between two parties. It's often used for creating access tokens.
Self-contained, what does that mean?
It means the token itself contains information, the claims, about the user, like their user ID, maybe their roles or permissions, and an expiration time. A JWT has three parts separated by dots: a header, a payload containing the claims, and a signature. The server generates the token, signs it using a secret key, and gives it to the client.
And how does that help secure APIs?
When the client makes subsequent requests to protected APIs, it includes the JWT, usually in the authorization, bearer token header. The receiving API server can then validate the token simply by checking its signature using the known secret key, or a public key if using asymmetric crypto. It doesn't need to call back to a central authentication server to verify the token. All the necessary information is in the token itself. This makes JWTs very stateless and efficient, which is great for microservices.
But I've heard there's a catch with revocation.
That's the main trade-off. Because JWTs are self-contained and verified locally, they are difficult to revoke immediately once issued. If a token is compromised before it expires, it could potentially still be used. The common mitigation is to keep JWT lifetimes relatively short, for Zytess 15 minutes, and use refresh tokens, which can be revoked to get new JWTs.
Okay, so JWTs are the tokens carrying claims. What about OAuth 2.0?
OAuth 2.0 is an authorization framework. It's not an authentication protocol itself, though it's often used alongside authentication layers like OpenID Connect. OAuth 2.0's primary purpose is delegated authorization. It enables a user to grant a third-party application limited access to their resources hosted on another service without sharing their actual credentials, like their password, with the third-party app.
Like the login with Google or allow app X to access your Twitter feed pop-up?
Exactly those. OAuth 2.0 defines several roles: resource owner like you, client like the third-party app, authorization server, resource server, and various grant type flows like authorization code flow, client credentials flow, for how the third-party client can securely obtain an access token from the authorization server with the user's permission. This access token typically has specific permissions called scopes attached to it, for example, read profile, post tweet.
So OAuth 2.0 is the process for getting permission and an access token.
Correct. It standardizes the flows for securely granting and obtaining limited access.
So how do JWT and OAuth 2.0 fit together? Are they alternatives?
They are very often used together and are complementary. OAuth 2.0 defines the secure authorization flows for how a client application can obtain an access token representing delegated permissions. And very frequently, the access token that the OAuth 2.0 authorization server issues is actually formatted as a JWT.
Ah, so OAuth is the framework for the dance, and the prize at the end of the dance, the access token, is often a JWT containing the user info and permissions.
That's a perfect analogy. This combination gives you both a standard, secure way to handle delegated authorization, OAuth 2.0, and a stateless, efficient, self-contained format for the resulting access tokens, JWT, that works well in distributed systems.
All right, let's try to apply everything we've learned now. This has been a lot of theory and concepts. Let's take a practical example. If you were tasked with designing a ride-sharing service, something like Uber or Lyft, what are the key challenges you'd face right away, and how would you start to architect it using these principles we've discussed?
Okay, yeah, a ride-sharing service is a fantastic, complex example that touches on almost everything we've covered. The immediate challenges that jump out are massive scalability, millions of users, drivers, real-time updates, extremely high availability, people rely on it 24/7, very low latency requirements, especially for matching riders and drivers and showing real-time locations, and needing consistency for critical operations like ensuring a driver is assigned only once for a ride, handling payments correctly.
So, high stakes all around. Architecturally, microservices seem like a must.
Absolutely essential, I would say. You'd immediately start thinking in terms of microservices. You'd likely have an API gateway handling incoming requests from the mobile apps. Behind that, core services like a user service, profiles off, a location service tracking driver-rider locations, a matching service, core logic finding rides, a ride service managing the life cycle of a trip, a notification service, push notifications, SMS, and a payment service.
And how will they communicate?
For real-time communication between the client apps, driver-rider, and the backend, WebSockets would be heavily used for things like broadcasting location updates or ride status changes with low latency. For internal asynchronous communication between the microservices themselves, Apache Kafka would be a very strong candidate due to the sheer volume of events, location updates, ride requests, status changes, and the need for high throughput and decoupling.
What about the data layer? That sounds tricky with all the real-time location data and transactional ride data.
Definitely tricky. You'd likely use a mix of databases. For core transactional data where strong consistency is paramount user profiles, ride history, payment details, driver ratings, a reliable relational database like PostgreSQL, perhaps managed and scaled using cloud services, would make sense.
But what about the millions of constant location updates from drivers? Hitting a relational database constantly for that seems problematic.
Exactly. For that kind of high throughput, often ephemeral data, like the real-time locations of active drivers, an in-memory NoSQL database like Redis would be much more suitable. Redis has excellent built-in support for geospatial indexing and querying.
Geospatial indexing, how does that work?
It's critical for efficiently finding nearby drivers. Techniques like Google's S2 library, which Uber uses, or Redis's built-in geohashing effectively divide the Earth's surface into a grid of cells. You store driver locations indexed by their cell ID. When a rider requests a pickup, the matching service can quickly query Redis for drivers in the rider's current cell and adjacent cells, drastically reducing the search space compared to scanning all drivers.
Okay, let's dive a bit deeper into a couple of key flows. How would you handle those high-throughput location updates from drivers without overwhelming the system?
You decouple ingestion from processing using Kafka. Driver apps would publish their GPS coordinates frequently to a dedicated Kafka topic, maybe driver location updates. The location service would then consume messages from this topic at a sustainable pace, perhaps batching updates, and write the latest location into the Redis geospatial index. The driver app just fires the update to Kafka and doesn't wait.
You could even make the update frequency adaptive, like less frequent if the driver isn't moving.
Absolutely. Adaptive update intervals based on movement or status would be a smart optimization.
And the driver-rider matching logic, how would that flow work using Kafka and Redis?
Okay, so a rider makes a request via the app. The API gateway forwards this, perhaps publishing a ride-requested event to another Kafka topic. One or more instances of the matching service would consume events from this topic. For a given request, the matching service would query the Redis geospatial index for available drivers nearby. It would then filter those drivers based on criteria, vehicle type, rating, etc. Maybe call out to a mapping service to get estimated ETAs for the top candidates, and then attempt to offer the ride to the best matched driver, likely via the notification service, which might use WebSockets or push notifications.
How do you ensure consistency? Like, how do you prevent two different matching service instances from accidentally assigning the same driver to two different riders simultaneously? That seems like a race condition waiting to happen.
That's a critical consistency problem. A common solution is to use a distributed lock. Before a matching service instance attempts to offer the ride to a specific driver, it would try to acquire a short-lived lock, for example using Redis with a TTL time to live, on that driver's ID. If it successfully acquires the lock, it knows it has exclusive rights to offer the ride to that driver for a brief period. If another instance tries to acquire the lock for the same driver simultaneously, it will fail, preventing the double assignment. The lock automatically expires after a short time, the TTL, if the offer isn't accepted, making the driver available again.
Clever. And scaling this whole thing.
Horizontal scaling for basically all components. Run multiple instances of the API gateway, location service, matching service, etc. behind load balancers. Kafka inherently supports scaling by allowing multiple consumer instances, like the matching service, to process partitions of a topic in parallel. For the databases, you'd use read replicas for PostgreSQL, and potentially geo-sharding if the user base becomes truly global. Redis can also be clustered for scalability and high availability.
Wow, okay. That really brings together a lot of the concepts. Let's try one more. How about designing a real-time collaboration tool, something like Google Docs? That feels even more challenging with multiple people typing in the same document at the same time.
Oh, absolutely. Real-time collaborative editing is arguably one of the most complex distributed system design problems out there. The requirements are intense. Multiple concurrent users editing the same document, needing to see each other's changes and cursors in near real time, handling basic formatting, and ideally supporting version history. The absolute keys here are extremely low latency for updates and achieving strong eventual consistency. Everyone needs to end up with the same document state eventually, without corruption, even if their edits conflicted temporarily.
How do clients and servers even talk to each other for that kind of real-time interaction? Regular HTTP requests seem too slow.
Right. WebSockets are the standard choice here. They provide a persistent, bidirectional communication channel between the client, browser, and the server, allowing the server to push changes down to clients instantly without the client having to constantly poll. Low latency is paramount.
Architecturally, still microservices.
Likely, yes, though perhaps fewer core services. You'd have an API gateway, probably a dedicated collaboration service handling the core real-time synchronization logic, a document service for document CRUD, create, read, update, delete, storage, and versioning, and a user service for authentication and user profiles.
Okay, but the absolute core challenge must be handling those simultaneous edits without messing up the document. How is that solved?
This is the heart of the problem, conflict-free concurrency. There are two main approaches, operational transformation, OT, and conflict-free replicated data types, CRDTs.
OT first. Google Docs uses that, right?
Yes. Google Docs famously pioneered the use of OT at scale. The basic idea is that edits are represented as operations, like insert A at position 5 or delete characters from 10 to 12. When a client makes an edit, it sends the operation to the central collaboration service. If multiple clients send operations concurrently, the server has logic to transform incoming operations against conflicting operations it has already processed, ensuring they can be applied in a consistent order on the server's master copy of the document. It then broadcasts the transformed operations back to all clients.
Sounds complicated.
It is notoriously complex to implement correctly, especially handling all the edge cases and concurrency scenarios. Getting the transformation functions right is hard.
What about CRDTs? Are they simpler?
CRDTs are a newer approach. They are special data structures designed from the ground up to handle concurrency differently. Edits made using CRDTs can be applied in any order, and the data structure guarantees that all replicas will eventually converge to the exact same state automatically without needing a central server to perform complex transformations. This can significantly simplify the back-end logic.
So why doesn't everyone use CRDTs? Is there a downside?
The main potential downsides are that CRDTs can sometimes have higher metadata overhead, making documents larger compared to OT, and the range of data structures and operations they support might be slightly more limited, though this is rapidly evolving. For this design exercise, let's assume we're using OT with a central collaboration service, similar to the classic Google Docs approach.
Okay, sticking with OT, how does the real-time edit propagation work in that model?
A client sends its operation, insert X at position 20, via WebSocket to the collaboration service responsible for that document. The collaboration service receives it, transforms it against any concurrent operations it knows about based on operation history versions, applies the transformed operation to its authoritative in-memory copy of the document state, and then broadcasts that transformed operation out to all other clients currently editing that same document via their WebSockets. Clients receive the transformed operation and apply it locally to their view of the document.
How do you scale that collaboration service? If one document gets really popular with many editors, won't a single server instance become a bottleneck, handling all the WebSockets and OT logic?
Absolutely. You need to run multiple instances of the collaboration service behind a load balancer, but now you have a new problem. If client A connected to instance 1 makes an edit, how does instance 2 know to broadcast that edit to client B who happens to be connected to it? They don't share memory.
Right, you solved that. Sticky sessions.
Sticky sessions, forcing all clients for one document to the same server instance, can work but limit scalability and resilience. A better approach is to use a back-end pub subsystem, something like Redis PubSub, which is very fast for this, or even Kafka. When instance 1 processes an operation for document XYZ, after applying it locally, it publishes the transformed operation to a specific channel or topic for document XYZ, e.g. docupdates.xyz, in the pub subsystem. All other collaboration service instances, like instance 2, subscribe to relevant document channels and receive the operation almost instantly via the pub subsystem, allowing them to then broadcast it down their own WebSocket connections to their connected clients like client B.
So the pub subsystem acts as a high-speed internal message bus, connecting the collaboration service instances for document-specific updates. That allows seamless horizontal scaling.
Exactly. It decouples the instances while ensuring all clients get all updates.
And where is the document actually stored? The collaboration service keeps it in memory for speed, but it needs to be saved somewhere durable.
Right. You'd likely use Redis again to hold the active document state, or at least the recent operation log, in memory for the collaboration service to perform OT against with very low latency. But for durable persistence, you'd store the authoritative copy, perhaps as periodic full snapshots plus the intervening operations, deltas, in a more durable NoSQL document database like MongoDB or maybe DynamoDB. MongoDB's flexible schema could be well suited for storing complex document structures.
And version history, how would that work?
Version history could be implemented by storing those periodic full snapshots combined with the ordered sequence of operations, deltas, applied between snapshots. Restoring a previous version would involve loading the nearest preceding snapshot and then replaying the operations up to the desired point in time.
Wow, okay. From the foundational laws like CAP, through architectural choices like microservices and EDA, scaling databases with replication and sharding, managing load, caching effectively, all the way to the intricate details of designing something like a ride-sharing service or a real-time collaboration tool. This deep dive has really given you, the listener, a powerful understanding of the core principles, the key components, and the operational mindset needed for truly robust system design.
It really touches on the fundamental trade-offs and patterns that engineers grapple with every day when building systems that need to handle scale and stay reliable.
So what does this all mean for you? Well, the next time you effortlessly stream a movie, book a ride instantly, or collaborate seamlessly on a document with colleagues across the globe, maybe take a second to consider the incredible layers of sophisticated design and engineering at play beneath the surface.
How might you start to look at the apps you use differently now, understanding the hidden trade-offs their creators had to make? Recognizing the patterns, like caching or asynchronous processing, that allow them to feel so fast and responsive.
It's not magic, but it's certainly impressive engineering built on these foundational concepts.
Yeah.
And this is really just the beginning of the learning journey, isn't it?
Oh, absolutely. For those whose curiosity is piqued, there are fantastic resources out there to delve even deeper. Top engineering blogs from companies like Netflix, Uber, Meta, Amazon, they often share detailed case studies. Online courses dedicated to system design prep, platforms like designgurus.io or ByteByteGo offer structured learning. And there are countless system design interview practice questions online that force you to apply these principles.
It's a fascinating field where the art and science of engineering truly come together. Until next time, on The Deep Dive, keep diving deep.